Wireless networking. This is absolutely a fantastic topic for a couple reasons. Number one, it's interesting, and second, it's very, very popular. We're going to break this up into two nuggets. We're going to do part 1 of 2 and 2 of 2. So let's jump into part 1 of wireless networking. So we're going to start off by taking a look at, first of all, how wireless local area networks operate. And that's the acronym right there, Wireless Local Area Network. Fairly high speed, fairly small geographic location, and how it all works. See, as a customer, if you and I walk into Starbucks or McDonald's and we bring up our laptop and it connects to the internet, we think, oh, that's fantastic. But you know what? Behind the scenes, somebody had to set all of that up for us. And that's what we're going to learn how to do in this nugget right here is we're going to understand the concept of how wireless local area networks operate, and then we're going to take a look at all the standards and acronyms associated with it. Sometimes the vocabulary, when you're starting to learn a new technology, if you hear some terms you're not familiar with, sometimes that can be a stumbling block. So instead of having stumbling blocks, we're going to turn them into stepping stones by making sure we understand the acronyms that are very similar. For example, I'll just give you a heads-up sample here. WEP, WAP, WPA, and those are all 3-letter acronyms that you're going to see all the time in dealing with wireless. So we'll sort those out, make sure you're comfortable with those acronyms so we can progress. There's also a whole set of standards. Now standards, I usually joke about this, is that the good thing about standards is that there's so many to choose from. However, with standards, if company A and company B are both making wireless products and they're following the same standards, guess what? Those two devices, either network interface cards or network devices, if they're made by each vendor, they should be able to talk to each other successfully. And that's the goal. And so we have some committees that help set standards, and we also have certification groups that make sure that vendor A and vendor B both created their product to the appropriate quote-unquote standard. So whenever you think of standard, I like to think of protocols in the case of networking. And again, what are protocols? Nothing more than rules. So we're following the same sets of rules. Why? Because we want devices to talk to each other. So once we've taken a look at those, we'll then plan for wireless. Now, some people's planning goes like this. Just throw it in and hope it works. And for a lot of homeowners, that's what they do. And when it doesn't work, they call somebody, a friend or what have you. You may be that friend they call in the future where they ask, hey, my wireless isn't working. Can you help me? Oh, sure. Keith and I will be right down. And you go help them. So we're going to plan out the wireless, and then we'll take a look at configuring the wireless from scratch. And to do that, I'm going to do two things. Number one, I'm going to show you how to set up wireless like in a home, in a small office or a home where there's like one access point. That's another acronym we'll take a look at. But a simple, small network that's using wireless for connectivity. And then we'll take a look at how we would do it in a larger organization. So I just got back last week from configuring a very, very large wireless network installation, and it's quite different from a single home or a single office installation. But the basic concepts are going to carry you forever. So we're going to focus on the core elements of both of those as we proceed. So without further ado, let's take a look at how wireless local area networks actually work. So here's the network that we're going to build up to. But let's start off with a simple analogy or an example of how wireless networks operate. Let me introduce you to my home network. At my home network, I have a service provider that I use, and that service provider connects me into the internet. So that service provider delivers at my house. I have cable. So I have a cable that comes in, and it goes to something called a cable modem. Just like that. So I've got the cable modem that understands how to talk with the service provider, and that cable modem has another connection that goes to my router right here. So I'm going to use these concepts in a small environment, and then we'll apply them to bigger as we come up. Now, for my router has a switch, and that switch happens to be built in. So there's a 4-port switch built in, and then I can take my PCs. Let's say I have 4 PCs, and I plug them all in to the switch ports. And so I've got one network here. So every interface on a router is a logical network, and these 4 switch ports, although they're built into the physical router, are acting like a separate switch. So the router has one network over here, we'll call it my home network, and one network out here going to the internet that connects to the service provider network. So great. So my PC, I'm a happy user, I have access. Well, Keith, how exactly is that wireless? Well, it's not yet, but I want to make sure we're on the same sheet of music. How does this happen at the house? Every computer has a network interface card, and that network interface card is responsible for the sending of the bits over this copper wire to my switch, and then my router makes forwarding decisions to the internet, just like we discussed in our previous chapters. So one day, somebody came up with the idea of, well, what if I don't want to be physically tethered, physically connected to my network? What if I want to be wireless? For example, maybe I've got this router in one room of my house, and I want to be able to go ahead and use the internet from the patio or from another room where there's no physical connections. What we could do is we could add a radio to the router. A radio? What do you mean? Well, it goes like this. On the router, and a lot of home-end routers have these, we simply add a radio transmitter receiver. So I'm going to put a little symbol there for radio transmitter receiver. And a radio, as you know, with like FM radio or AM radio, you can turn your radio to a certain channel or a certain station and listen to the music. Well, with radio technology, what we can do, instead of using this copper, we can have the router send the signals wirelessly, and we can have our clients, let's say I have my client in the other room, that he's happy because he has a wireless adapter that can also send and receive signals. And instead of using copper, this now mobile computer can communicate with the router using wireless. So that's how it works. Now there's a couple of gotchas that we definitely want to be aware of with wireless. Number one, we're using a radio frequency. And what happens if two radio companies start advertising on the exact, or start setting their broadcast on the exact same frequency? The answer is they would run into each other, the music would be all messed up, it wouldn't work. So we have to make sure that the radio frequency that we're using for our wireless isn't going to interrupt anybody else. The other thing I want you to be aware of is that in an Ethernet network like down here, where we have a copper cable, we have 4 wires. And with a switch, if this is a built-in switch right here, we're using 2 of those wires for sending data and 2 of those for receiving. And check this out, we can use full duplex. So on wired networks, we have full duplex. And why is that handy? It's handy because we don't have to worry about collisions, because there won't be any on a wired network because we're operating in full duplex. Now, however, if we move over to wireless up here, if I have 3 PCs down here, that guy's unhappy, he's mediocre, and he's happy, and they all have wireless network interface cards, and they're all communicating on the network, guess what? If we're all using the same radio frequency, you can only have one device talk at a time on a wireless network, and that is the case. So wireless is always going to be half duplex. I say always. For our purposes, wireless is going to be half duplex in the fashion that we're using it for our wireless local area networks. Half duplex means that only one device can send at a time. If 2 people try to talk at the same time on the same frequency, it's going to cause a problem with understanding the actual bits that are being sent. So instead of with Ethernet, if we were going to use like a hub, which we're not anymore, but if we were, we'd use carrier sensing multiple access with collision detection. That means we're listening for the wire, making sure nobody else is there, and we send. With full duplex, we can turn off CSMA CD because we don't need it. In full duplex, we're super happy. We have all the bandwidth we need as far as sending and receiving at the same time, so we disable carrier sensing multiple access with collision detection. If we go over to this side of the house, over here to wireless, we are going to be operating in half duplex, and we're going to use carrier sensing multiple access with collision avoidance. Now, this is not very nice, but collision avoidance is basically making sure that the real traffic we're going to send doesn't have a collision. And it works something like this. Let's say you and I are on a wireless network, and we both want to send some bits on the wireless network at the same exact time. Well, before we start sending those bits, we're going to send a little test shot across the wireless network. And if that test shot across the network makes it successfully, we know there's a window for us to go ahead and start our communication, and there won't be any collision of the real data. So carrier sensing means we're still paying attention, listening to who else is talking. Multiple access means there's three or more devices on that shared medium. And collision avoidance means using our little test shots. I used to tell an analogy, I get a little trouble for it, but it's like standing on the corner of a busy street, looking both ways, and then sending a younger sibling across the street first. If they make it because you can run faster, you can make it with no problem. But you are sacrificing the sibling. Okay, that's mean and cruel, but that's how it works. A good way to remember it. So, local area networks with wireless. From just the concept here, you need a radio. You need a radio on both ends. So if you're going to use a radio on the router, you need a radio on the PCs. That's usually built in as part of their network interface card. They need to find the right channel, or if you will, the right frequency to communicate. They're going to be operating in half duplex, and they're going to be using carrier sensing, multiple access with collision avoidance to do it. All right, so now that we've taken a look at the concepts of, okay, basically, Keith, we hear what you say is you're swapping out copper, the actual wires, for wireless. So layer 1 and layer 2 of the OSI reference model, we're swapping out the copper and the protocols there for wireless. Layer 3 and higher, guess what? None of that has to change. All we're doing is swapping out layers 1 and 2. So let's start with some terms that definitely we want to be comfortable with. The first of those is Wireless Local Area Network, or WLAN. A lot of times people confuse that term when they hear it or see it, because there's another term that looks very much like that, and that is WAN, Wide Area Network. That's where we have some geography, a lot of it between two sites. So if this was in Las Vegas, Nevada, and we had a remote site in Reno, just for a moment here, we would consider this a wide area network connection. So when you see WLAN, if you read it fast, it kind of looks like, WAN. So what's the biggest difference between a wired network and a wireless network? And the biggest difference is two things. I'd like to share them with you. Those two things are layer 1 and layer 2. Now, in our discussion about OSI reference model, we talked about the layers of the OSI reference model, what they do and how they operate. And we learned a couple things. We learned that at layer 1, it's responsible for bits, sending bits on the wire, receiving bits on the wire. In the case of wireless, it's responsible for receiving bits on the radio frequency that we're using or sending the bits. Also at layer 2, there's rules for layer 2 things such as framing and accessing the media. When do we get on? What does the frame look like? How many bits do we put in? What order we put in? And it's no magic that wireless networks can operate, because there's a standards group that's responsible for creating all these standards for layer 1 and layer 2, and it's the IEEE. Now, the IEEE is another acronym, and it stands for the Institute of Electrical and Electronic Engineers. So you don't have to actually memorize the full name of the group, but you should be responsible. These are the people, the groups of people that are responsible for the protocol standards at layer 1 and layer 2. For example, on Ethernet networks, so here we have a switch, we have some wired connections coming in, a router's wired in. On an Ethernet network, there is a 802.3, and what that represents is that's a working group within the IEEE. And you know what they love to do? They're all about Ethernet networks. They make the standards for it. So if company A and company B both make network interface cards and they want to be compatible with everybody else making network interface cards, they'll make sure that the framing and the bit spitting and the bit receiving that are done on their copper network interface cards are all done based on the protocol standards. So the 802.3 group is all about Ethernet networks, layer 1 and layer 2. That's who sets the rules. It's the IEEE and this working group inside the IEEE. Now, 802.11, let's take a look at that. The 802.11 group is all about wireless. So the standards for layer 1, which is radio frequency, and layer 2, which is the standards for framing and so forth and getting access to the network, are all done by 802.11. Now, this is kind of fun too. There are so many flavors and variants of wireless that it's not just one group. They've actually subdivided it into specific areas. So you might see something like, let's get a different color. Right here, there may be a different letter. For example, there's 802.11a as one standard and 802.11b 802.11b as another standard, and 802.11g, and 802.11n. That's an N. So these are the standards. So what's the best one to use? That's so easy. The best one to use is the one that's compatible between your network devices. So all of your devices on the same local area network with wireless need to be able to speak a common language if indeed they want to communicate with each other. So 802.11, whenever you see that, just simply think to yourself, oh, those are the standards for wireless. And there's usually some lowercase letters following. So let's take a look at how we can make friends and not ruin somebody else's wireless signals in close proximity. We can use something called channels. Now, this is important because if we are using the same exact frequency as somebody else, we're going to mess up their signals, which is not nice, but they're also going to mess up our signals. So here's what we're going to do. If we're going to set up wireless networks in the 2.4 gigahertz range, when we talk about the 2.4 gigahertz range, it really is a range. It's not like literally just one frequency that's the same. It actually goes from like 2.4 into 2.5, and it's across a spectrum. So let's say this is the entire spectrum of the 2.4 band. You know, like a band, like a grouping, like the Beatles or something else. So we have a band. The 2.4 gigahertz band is a range of frequencies. Inside that range of frequencies, we have channels. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and also there's some higher numbers out to the right that in the U.S., we can't actually use. They're not allocated for that purpose here. In other countries, we can use channels higher than 11. But let me tell you about these channels. Unfortunately, each of these channels overlaps with something else. wait a second, Keith. You're saying if I take channel 1 and my neighbor takes channel 2, we're still going to be overlapping? Yes, because each of these channels actually is using a range as well. So we have the 2.4 gigahertz band, which is a large range, and each channel which uses a smaller range. So Keith, how do I avoid conflicting with my neighbor? Tell me. And the answer is simple. We need to know how far the ranges overlap with each other. So what I'd like you to do is I'd like you to write out 1 through 11, just like I have right here, and I'd like you to draw a little boundary over 1, 2, and 3, and that's channel 1. Channel 1 is going to overlap with channels 2 and 3. Next, I'd like you to go ahead and put a little overlay, a range, all the way from 4 to 8. And we're going to say channel 6 is right there. Channel 6 overlaps with 4, 5, 7, and 8. And then we'll go to one last one. I'll put an arrow there. And that would be channel 11. The way that you can avoid overlapping with anybody else in the 2.4 gigahertz range is simple. Is first of all, do a site survey, meaning find out what else is on the network. We'll take a look at that together. And then choose a channel that is not overlapping with them. So if my neighbors were on channel 1 and channel 6, and I knew that they were not on channel 11, or the weakest wireless I could see was on channel 11, I would want to choose channel 11. So in the US, the channels we would choose are channels 1, 6, or 11. And if you have 2 access points, you wouldn't want to go ahead and overlap them with each other. So that's pretty straightforward with 2.4. In the 5 gigahertz range, we have a whole bunch of non-overlapping channels. So if we have a situation with a condo and you've got 200 tenants and 100 of these tenants all have wireless access points, you might want to purchase a wireless access point or a wireless router in the 5 gigahertz range, because the 5 gigahertz range has dozens of non-overlapping channels. So you can do a site survey, which means a fancy word for finding out what else is out there by listening to the wireless, and then simply picking a channel in the 5 gigahertz range with your 5 gigahertz capable wireless router that's not, the same as anybody else in that 5 gigahertz space. That's how you do it. All right, so that's the concept of bands and channels. Next, what about the problem of vendor A and vendor B? They're both vendors. They're both making wireless network interface cards. Maybe one of them makes a wireless interface card for the PC. Another one makes a wireless interface card for the tablet. Another one, vendor C, is making wireless access points. Now, a wireless access point is nothing more than a device that is converting, if you will, the wired signals on copper is tied into the network into wireless so that the wireless clients can get access to the network. So we have layer 1, layer 2 here, which is specified by the 802.3 group from IEEE. Thank you very much. And the wireless portion is 802.11 something based on the actual technology you're using. 802.11n or 802.11b or 802.11g, etc. So how do we make sure the vendors are compliant, meaning vendor A, vendor B, vendor C, all their devices work together? And the answer is the Wi-Fi Alliance. The Wi-Fi Alliance is an organization that does certification of products. So if vendor A, vendor B, and vendor C all go to the Wi-Fi Alliance and they bring their products and saying, hey, we're conforming to the 802.11n standard as an example, the Wi-Fi Alliance can, for a fee, verify their products are behaving properly, sending the bits, receiving the bits, the radio frequencies are working as they should. They get their stamp of approval, and that's what most of our vendors use today. They use Wi-Fi Alliance certified products, meaning they manufacture product, get it certified by the Wi-Fi Alliance. The WAP, coming down here, the WAP is nothing more than a wireless access point, an access point into the network. And the primary job of an access point is to convert. Convert what, Keith? To convert wireless standards at layer 1 and 2 into copper, Ethernet 802.3 standards. And that's primarily what it does. It's the liaison, if you will, for the layer 1 and layer 2 between a wireless client and the network. Many routers have that wireless piece built in, and also many routers have the switch built in as well. So you could look at that little box and say, what is it? Well, it's an access point. Well, it's a switch. Well, it's a router. And it would be all true. And today you can get a low-end device like that for less than $50 US. Very, very, very affordable. All right, that's what a wireless access point is. So our next topic here is, well, tell me about these things right here, these antennae. So what about antennas? What do you need to know about an antenna? The antenna is the physical layer portion, if you will, that allows us to send and receive bits. In a data network, we're all talking about bits at layer 1. So we're sending and receiving bits, and there's two types of antennas that I like to focus on. One is omnidirectional. Now, what is omnidirectional? Omnipresent. I mean, omni is everywhere. So let's say this was our building or our home, either way, and we wanted the access point to have reach to everywhere. If we purchased an omnidirectional wireless router or access point and we put it right here, it would equally cover the whole entire house, or as best it could. So omnidirectional sends and receives in all directions. The other side of the house is unidirectional antenna. And why would we want to use one of those? Well, let's say this is our company. And let's say also that this is a parking lot. I'll label it. That'll help. Parking lot. In the parking lot, we probably don't want our wireless signals to go out to the parking lot. Now, if we wanted to be very safe about that, we could put access points right here with antennas that only send the signals this way and nothing out to the parking lot, if you want to control where that signal goes to. Now, having said that, having this unidirectional here and omnidirectional here, we still have the issue with some interference. Now, what can cause interference with wireless? Well, there's a lot of things. Number one, anything physical. What do you mean, Keith, anything physical? Well, if I have walls in my building, those walls are going to degrade the signal. And if I have lots of walls, the signal is going to be degraded to a point where it won't be usable. So even though my customers can connect at various speeds based on the technology, the actual throughput is going to depend on how good the actual signal is between the client and the access point that they're associated with. So we also have things like filing cabinets that could cause a physical interruption of the signal. Generators with heavy-duty electromagnetic interference could affect that as well. We could have telephones because we're in the 2.4 gigahertz range, or if we are, and we have a telephone in that same frequency, it's possible that that telephone could interfere with us if it's a wireless telephone. Microwave ovens have been known in the past to interfere as well. So we want to make sure that we understand that the access point or the wireless radio inside of a wireless router has the ability to send signals. Most homeowners are going to have the omnidirectional, and the unidirectionals are going to be more expensive and take a little bit more to configure and strategically place so everyone in the company has access while the signal doesn't leak outside. So let's take a look at a customer joining a network. Let's say for a moment that we don't have these two APs, we just have one, and this AP is going to advertise what's called a service set identifier, SSID. And the service set identifier is the name of the network. That's all it is. So if the name of the network is Wireless Local Area Network 1, when the client looks at his options for wireless networks, he can pick that one and do something called associate with that specific access point. So all his communication now on the network is going to be through this access point, which is doing the conversion, if you will, from layer 1, layer 2 here, and then it's going from layer 1, layer 2 here, back and forth on the network on behalf of the client. So that's all it is. So a service set identifier. Now there's several types of service sets that we can use. We can use an independent service set. And what an independent service set is this. Let's say we have just one PC here and another PC here. They go to the library. There's no physical network. And let's say they're actually at the park. That's even a better idea. So we're at the park. There's no electronic outlets or anything, just their two laptops. And they want to communicate with each other. They could build what's called an ad hoc, on-the-fly wireless network. And the technology or the concept would be an independent service set, meaning it's independent of any kind of access point or infrastructure. They're simply using the wireless adapters on their computers, on the built-in network interface cards, and they're able to build an ad hoc network using independent service set. If we wanted to move up the food chain a little bit and we want to do something like this, we could put in a physical access point, physically wire it to our network, and we could advertise an SSID, and that would be called a basic service set. You could also call it basic service set identifier. So now you're not all alone in the park with another computer. Now you've got a corporate resource, an access point, that's giving you the control of saying, okay, this is an access point, here's its name, you can connect to it. The basic service set is also called infrastructure mode, because you've got an access point in the infrastructure in your corporate network that you can connect to. So if you hear about service sets, the concept is the independent service set has no access point. You're just using the built-in network cards. It's an ad hoc network on the fly. If you're using a single access point, you're using basic service set identifier, which is identifying a single access point. Now, I realize that most of you are planning and preparing or maybe in corporate environments where you have large areas to cover with an access point. So how do we do something like this? Let's say this is the one floor of a building, and we've got a whole bunch of offices on one side, maybe a conference room over here. We have the elevators in the middle, break rooms, filing areas, etc. Maybe some more cubes out here. So we have a fairly large area, and we discover that, oh no, if we put an access point right here, we'll call it access point 1, it only covers maybe this much of the building. So what do? Well, the answer is you could put in a second access point. We'll put them in a different color here. So we put in access point 2 right here, and he covers this, and we'll put in access point 3. We'll do them in this color. And he covers this. So the key is we want to make sure that everybody's covered. So no matter where a user goes on the floor, they'll have access to the wireless network. Does that make sense? Right. So the challenge with this, though, is if we do this network, we don't want to overlap the channels. So if we were going to do this correctly, maybe this would be channel 1, and this access point would be channel 6, and this access point would be channel 11. And that way, they're not going to be harming each other. In fact, we could do 1, 6, and 1 again, because the signals from access point 1 won't overlap with access point 3, and we'd be fine. But you want to plan that out ahead of time to make sure you're not overlapping. But the point I want to bring out here is one third type of service set is called the extended service set identifier. And that's where, and let's say this is AP1, AP2, and AP3. They're all supporting the users on this floor of the building. What I could do is use all these, have every one of them advertise the same service set identifier. So I could call it WLAN 1, WLAN 1, WLAN 1. So each of the users, when they connect, they're going to connect, they're only going to see one service set identifier called Wireless Local Area Network 1, and they're going to associate with the access point behind the scenes that has the strongest signal. So if they're at this end of the building, they'll probably associate with access point 1. If they're on this end of the building, they'll probably associate with access point 3, and that's how the magic works. So with service sets, independent service sets is 2 devices creating an ad hoc network. If we have 1 or more access points, it's called infrastructure mode because we have physical access points in place. And if we have 2 or more access points with all the same service set identifier, it's an extended service set. Another really cool feature that we have in corporate America is something called a wireless LAN controller. And why is it important is for this reason. Let's say I have to roll out, you and I have to roll out 3 access points, or 300 for that matter. Instead of having to go configure each one of those with all the specifics for what channel to use and what the SSID is going to be, we can have a physical box called a wireless local area network controller. I'll just call it WLC for short. And we can have all the access points check in and report to this wireless local area network controller. With that, you and I, we sit here at this PC and we configure the wireless LAN controller. We say, you know what? I want the SSID to be our net 5. And that will be the new SSID. And he'll tell all the access points, and poof, in about less than 60 seconds or whatever the time interval is, you'll now be advertising that new SSID. Another thing about a wireless LAN controller is that if you need to worry about the channels not overlapping, it can automatically know all the channels that are in use by those access points, and it can go ahead and adjust automatically. So maybe it's going to use channel 1 here, channel 6 on that one, channel 11, and we don't have to manually configure it because the controller knows exactly what the access points are set to. It can also tell what frequencies it's receiving and can adjust all of that in the background. Some pretty amazing stuff. So I'd like you to do a little exercise with me. It'll be worth your time. It'll help you remember a few of the standards. We already know that the 802.11 group is responsible for wireless. And what I'd like to share with you is a couple of the specifics that you definitely want to make sure you're familiar with that we use on wireless networks today. So we have 802.11. Let's start off with B as in boy. We have 802.11, and we'll go A as in apple. And we have 802.11, G as in girl, and 802.11, N as in Nancy. I'd like you to jot those out. Now, the way I remember those is Baggin. Like Bilbo Baggins? I don't know. Whatever can help you remember those 4 flavors of wireless, which we're going to discuss, that would be a good one just to make sure you're comfortable with those 4 different methods. So 4 different standards, all from the 802.11 group. So how fast are these different technologies as far as from the client to the access point? Now, the access point could be built into the router or it could have a separate access point. Logically, it works the same. So with 802.111b, we'll say the rate, the data rate, is somewhere between 1 and 11 megabits per second. For A, 802.11a, it's somewhere between 6 and 54 megabits per second. You might say, well, what do you mean between? How does that work? A client's going to adjust automatically based on how good the signal is. The further the client is away from the access point, or if there's disruption to the signal, what have you, or it can't get a clean signal, it's going to slow down as far as its throughput so it can go ahead and have clean data that's being sent. So the further you are away from an access point, the client is, the slower the data rate's going to be that it's going to negotiate. Okay, with G, we have 6 to 54 also, megabits per second, Mbps. And 802.11, you're going to like this, somewhere between 7 and 300. And let's put on there also that we're going to do something called bonding, like James Bond. We'll come back to that in just a moment. But that's the ranges. So as far as the technologies, here's the good thing. Somebody else wrote all this, and they made it all possible. The IEEE created the standards, vendors implemented it, the Wi-Fi Alliance certified them, but we should be vaguely familiar with some of the capacities of them. So these were released, B and A were released in the 90s, and G is more recent, and N's the most recent. So they go left to right pretty much chronologically. The actual frequency, the band that they're using, again, in the 2.4 band frequencies, we have the channels, and those channels overlap with each other. So if we want clear channels, we'd use channels 1, 6, and 11. Those completely are separate from each other, and they don't have any overlapping. So really, in the United States, you should use 1, 6, and 11. If you're outside the U.S., where they allow like channel 13 and so forth, that also may be a possibility there. So for the actual band, the frequency 802.11b is 2.4 gigahertz. You need to jot these down with me. 802.11a is in the 5 gigahertz range. 802.11g is also 2.4 gigahertz. So G is backwards compatible with B, by the way. And then up at 802.11n, it can do 2.4, and it can also do 5 gig, depending on how you configure it. So there you go as far as the bands go. And then one other piece I'd like to share with you, that's modulation. Modulation, what's that? Well, modulation is the process of how we put data inside something. So if we have a frequency that's going, how do you actually encode data? Do you skip a cycle, or do you change the voltage on if it's copper? What do you do to represent the actual data on the radio frequency? And the modulation types, I'd also like you to jot down because I think they may come up for you. We have direct sequence spread spectrum for 802.11b. So direct sequence spread spectrum. And you don't have to analyze the entire full name. You can just know that modulation uses DSSS. That'd be enough. And for 802.11a, it uses OFDM, orthogonal frequency division multiplexing. Again, just the acronym is enough. For G, it could use both, meaning DSSS and or OFDM. And for 802.11, it uses OFDM. Just different ways of, and it's all behind the scenes, nothing that we have to configure, but it's behind the scenes of how it encodes the data, the bits, if you will, onto the frequencies. And one other thing that 802.11 does, it has a thing called MIMO, multiple in, multiple out, where you can actually use 2 channels at the same time. So that's how we can get up to the 300 megabits per second. If you're using one channel with 802.11, we're going to get 150 megabits per second on a great day. And if we're bonding 2 channels together, it's possible we could actually double that. So all these numbers look great. Let me tell you that in your experience, your mileage may vary. Your mileage will vary, because it's all about how close is the access point to the client. What standards are we using? 802.11b, A, G, or N? Are we bonding multiple channels together or not? And how much interference is there? That's going to control a whole bunch. The other thing on top of all this, it's all half duplex. So just be aware that only one device can send at a time on this wireless network, because they're all sharing the same frequency. So everybody on this network, if it's 802.11, let's go with G, operating at 2.4 gigahertz, they're all sharing that space. So let's take a look at something that could go terribly, terribly wrong with our wireless network. Once we have an access point up and our client has associated with that access point, now we can communicate with the rest of the network using the access point as our middleman. Fantastic. What about this segment though, the wireless network. This guy and this guy can both listen in. There's no security by default with a wireless network. So we definitely want to address that. And let me give you a little history lesson. Many, many years ago, more than a decade ago, they decided to go ahead and create a standard called WEP. It stood for, I think, Wired Equivalent Privacy. So they thought, yeah, you can be wireless, but we use web security to protect and encrypt the conversation between this PC and this access point so that anybody trying to eavesdrop wouldn't be able to make sense of their conversation. Fantastic. Well, unfortunately, it's broken. When I mean broken, it means that somebody with a hack tool can go in, eavesdrop on the network, and determine very quickly, in less than a minute or so, exactly what those WEP pre-shared keys are. Now, the term PSK is an acronym for pre-shared keys. And with WEP, you put a pre-shared key on this computer, you put a pre-shared key on the access point, and if you're using WEP, anybody who's eavesdropping could basically, in a matter of minutes, find out what that is. I've got a video up on YouTube if you want to check that out as well. So it's broken, so we don't use it. So they came out with a better option, which is called WPA. And with WPA, it uses something called TKIP. And you don't have to memorize what TKIP stands for. It does stand for Temporal Key Integrity Protocol. And so it's better, but unfortunately also broken. Somebody found a way to determine what that is, so it's not very secure. And then they came out with WPA2, and that's also known as 802.11i. And if you see 802.11i, they're talking about WPA2, and that uses something called CCMP for data integrity of the individual bits and frames that are sent. It also uses AES, the Advanced Encryption Standard for security. So we have the benefit of CCMP and AES, and this one is the current one that you'd want to use today. So here's a history lesson. No, no, yes. So WEP was broken, WPA is broken, WPA2 is what we want to use. There's also, on top of that, a couple of flavors. So with WPA, let's say we're going to use just WPA2 for the encryption of the traffic between the client and the access point. If we were going to use it in a smaller environment, we could use something called personal. What do you mean personal? Well, personal, you're going to put a pre-shared key on the client, a pre-shared key on the access point, and they're going to use that pre-shared key as they develop their privacy between the access point and this client, and between the access point and this client, and so forth. So we use a pre-shared key on both sides. The other option is called WPA2 Enterprise, like Captain Kirk. Enterprise. ENTERPRISE. Doesn't look right. ENTERPRISE. It still doesn't look right. All right. So Enterprise. So WPA2 Enterprise, what that means is this. Instead of having a pre-shared key on the computer and on the access point, instead, what's going to happen is when a client associates, so we'll call this a client, when he associates with the access point is going to use something called 802.1x. Now, this is not 802.11x. It's 802.1x. And what that means is that the access point is going to say, oh, I need to know who you are, Mr. User, before I let you on the network. So we're not just relying on a pre-shared key. We actually ask the user who they are. The access point then talks to a server who knows who everybody is and asks the server, hey, dear Mr. Server, I've got Bob who's trying to log in, and say Bob's trying to log in. And here's the password he gave me, and is he a valid user, yes or no? And if the answer is yes, he's a valid user, this server can actually tell the access point what keys to use to encrypt the data between the client and the access point. So it's like an amazing difference in security. It goes way, way up. So effectively, the client authenticates, proves who he is with the access point. The access point verifies the user against a server on the backside. This could be, for example, a Radius server. We'll talk more about that in another nugget. But a Radius server, and the Radius server says, yep, Bob is a valid user. He put in the right password. And the Radius server could feed back the keys to use to allow the user to go in. So we're not using a pre-shared key across the board. We're actually using the authentication of individual users. So what do you need to pull away from all that? Here's what you need to pull away. WEP uses pre-shared keys on both sides and it's broken. WPA is a little bit better because it uses TKIP, and WPA2 is the best. You can do it in personal mode, or you can use it enterprise mode. ENTERPRISE. And in personal mode, you use a pre-shared key on both sides. And enterprise mode, you use the username and password that have to be known by the corporate network so that the user can authenticate. Another name for WPA2 is called 802.11i. So there you have it. Let me just do a quick check here, make sure I got all the concepts. Wireless local area network. Yes, IEEE, the standards group, specifically 802.11, the individual bands and channels inside of the wireless, the Wi-Fi Alliance for certification of vendor products, the wireless access point, allowing access to the network. It could be built into a router. The antenna types could be omnidirectional or unidirectional. Service sets is a fancy name for the name of the wireless network you want to connect to. And security, we have the old, and what we're going to use in a production environment. So now that we've taken a look at how wireless networks operate, and we've taken a look at the acronyms and the standards that make it all possible, in the next part 2 of this nugget, we'll take a look at the actual planning and implementation from the ground up of our own wireless network. I hope this has been informative for you, and I'd like to thank you for viewing.